Okay. So any questions about our new unit as we are moving along? I'm watching Olivia. She has her Unit 3 assignment sheet out. That is the time where, now that we are finished with that unit assignment sheet, that is the time that you can fill out all those special cool things and turn it in for that extra credit. Keep in mind the pictures on the back, you don't know everything yet, but these are the things that we're getting to. And as we get to them, pay attention to the pictures, and that reflection piece helps you think about what you're thinking about, why you're thinking about it. Sound okay? Questions on how these colored pieces of paper work? Questions about the extra credit? Questions about when to turn them in? Okay, but I don't want you doing it now. So now that class has started, Olivia's going to put that away because she knows she needs to pay attention to this. Hey, my key was a mess. I'm hoping that you took the time to get a spare extra piece of paper out and do your work, because when I tried to do my work on this, it ended up getting really crunched up. All right, so what I'd like you to do is, we're just going to quickly go over this. This cumulative review was your opportunity to go back and dig into Unit 1, do some segment addition postulate practice. Number 1, the length of EG is 8. Number 2, HI is 12. 3, GI 16. 4, EI is 24. 5 and 6, I'm just calculating the midpoints. Pay attention over here is where I put my work. If this is my end point and that's the midpoint, 7 plus some other coordinate value, x coordinate, divide by 2, the average of 7 and this mystery number was 9. Here's the math on how to solve it. Then I had to go get the y coordinate. 5 is my endpoint. 7 is the y coordinate of my midpoint. 5 plus some mystery, I don't know, divided by 2 was equal to that value, 7. So that's how I went ahead and solved it. So if the midpoint is this of AB, if this is A, that's the coordinates of B. Same work over here. Number 6 is over here. All right. With your group mates, please, would you share your answers to 7, 8, 9, and 10 while I walk around and give you credit for your hard work? And your mark is set, talk. Okay. Did you get it off of Schoology? Okay. So next time that you can't print, you can get a piece of paper and do the work on a piece of paper and still get credit for your homework. Because you know at the end of the day, it's all about not falling too far behind, right? Christian, has it done both sides? Half of it? Half or not at all? Sabrina done? Nazika done? Okay, about half of it. How would you reading? Yeah, but it was the Schoology and you just got by and we had you print and you could come and get the piece of paper, right? Were you here yesterday? Next time you need to go on Schoology. And get done homework Okay, so what are you going to do right now? Sit and look at a triangle? Or are you going to ask for a piece of paper? Did you go on Schoology? Did you check it? That's what you're going to do next time. Wait till we get there. I didn't even have her. Why? You have? Okay. How are you doing homework? Guys, done? Uh-oh. It's an organization.
Everything fell out of my folder.
Oh, no. Okay, how are we gonna write your name down? You tell me when you find it. Find it. Okay, Christian, done? Okay. We're not. All right, come back. Any questions on 7 through 10? Okay. Solving the equation 10 or 11 and 12, I did down here, and it's kind of like a little mini proof. And remember, I just want you getting good at being like, if somebody asks you, why, I need you to get used to being like, oh, because I'm going to add this value to both sides because the addition property of equality. I'm going to divide each side by 2 because the division property of equality. 11, I got x is 20, 12, x is 13. When we look here at these angles here, that 13 through 16 should have been easy because you just took a test on that stuff. So not a problem there. All right, let's talk about this proof. I kind of loved it. If I'm given those two lines are perpendicular, we go back to that unit 3 idea. What do I see? What do I know? What do I need? I need the sum of 1 and 2 to be equal to angle WYX. So because the lines are perpendicular, by the definition of perpendicular, each of these angles are right angles. So the definition of perpendicular defends that. Because they're right angles, I know their measures are 90 degrees. My angle addition postulate tells me that 1 and 2 added together are going to equal to the measure of angle X, Y, Z. So my transit property of equality allows me to put these two together. These two measures are the same, and then I'm going to go ahead and put the sum of 1 and 2 in for the one that it's equal to, and then I go ahead and I end up with my proof statement. So if you're keeping track of justifications in your proof pantry, make sure you have the definition of perpendicular, make sure you have the definition of right angles, the angle addition postulate, transitive property, and that's got to be of equality because it's numbers, not things. And then my substitution property equality. Questions on that, Jackie?
I have a question on number 12. Isn't x equal to 8?
Why did I say 13? Jackie, go Professor Marnie. Yeah, because do you know what I was thinking, Jackie? Look, I was up here at 26. Do you guys ever have that where your brain moves at a different speed? Is that better? I definitely like that better. Hey, and how about 6th period that didn't catch that? Whenever 5th period, whenever the next class catches a mistake that the other class didn't, I'm like, were they listening yesterday? Maybe not. All right. On the back, say the word Eratosthenes. Try again, Eratosthenes. Yeah. So Eratosthenes was this amazing guy over 2,000 years ago. He used parallel lines to estimate the Earth's circumference. Here is a little story about how he did that. So if I hit play.
In the mid-20th century, we began launching satellites into space that would help us determine the exact circumference of the Earth, 40,030 kilometers. But over 2,000 years earlier in ancient Greece, a man arrived at nearly that exact same figure by putting a stick in the ground. That man was Eratosthenes, a Greek mathematician and the head of the Library of Alexandria. Eratosthenes had heard that in Syene, a city to the south of Alexandria, no vertical shadows were cast at noon on the summer solstice. the sun was directly overhead. He wondered if this were also true in Alexandria, so on June 21st, he planted a stick vertically in the ground and waited to see if a shadow would be cast at noon. It turns out there was one, and it measured about 7 degrees. Now, if the sun's rays are coming in at the same angle at the same time of day, and a stick in Alexandria is casting a shadow while a stick in Syene is not, it must mean that the Earth's surface is curved. And Eratosthenes probably already knew that. The idea of a spherical Earth was floated by Pythagoras around 500 BC and validated by Aristotle a couple centuries later. If the Earth really was a sphere, Eratosthenes could use his observations to estimate the circumference of the entire planet. Since the difference in shadow length is 7 degrees between Alexandria and Syene, that means the two cities are 7 degrees apart on Earth's 360-degree surface. Eratosthenes hired a man to pace the distance between the two cities and learned they were 5,000 stadia apart, which is about 800 kilometers. He could then use simple proportions to find the Earth's circumference. 7.2 degrees is 1/50th of 360 degrees, so 800 kilometers times 50 equals 40,000 kilometers. And just like that, a man 2,200 years ago found the circumference of the entire planet with just a stick and his brain.
Kind of cool, yeah? Okay. So, if you look at what I asked you to do, on a day when that sun shone down, now my calculations are in miles and not kilometers. But that's okay. We can still set up the same proportion. And if we set up this same proportion, we can get that estimate for how far this small part, what fraction of the whole circumference of the Earth. Would you please, with your partners, use the diagram on your homework sheet and recreate the story that was on the video. On your market set, talk. Go. Use the picture.
Like they had no shadow, something. No. And you can measure
What did he
the
do?
distance. And then figure out
He put the stick in the ground. What do you notice about the stick? Shadow is different. So we measured the degree. And the degree here is the same as the degree there. Yep. So that's the really killer part that we need to see. So go ahead and on your picture, if you need to use the color pencils, here are the parallel lines. Check it out. Here are the parallel lines of the sun coming in. And he measured that 7-degree difference, and he calculated how that has to do with what portion of the Earth he has. So see that transversal? He created a system of alternating interior angles because here is my one sun ray, here is my other sun ray, and when he extends those lines and this transversal, can you see the alternating interior angles?
Yeah.
Here's the 7 degrees that he measured, and that same degree of that portion of the Earth. How about this guy? What was his job? Yeah. Have you ever been counting something and somebody interrupts you and you're like, oh, I gotta start over? Did he say like 8,000 stadia? I'm assuming, right? So can you imagine counting and being like, hey, where are you going? Oh, start over. That would be me. Yeah, I would definitely need a system of keeping track of my steps. But how cool was that? Parallel line systems, alternating interior angles, all a part of that conversation. I love it. Okay. Usually this is when some yo-yo raises their hand and says, is this on the test? No, it's not on the test. But what it is an application of what we're talking about. mathematicians that we talked about at the beginning of the year. And it's amazing. I was in Chicago this weekend visiting my son. The architecture in Chicago is crazy. Crazy. And I look at these buildings with these ornate embellishments, and they did that without the technology that we have today. Like, not even electricity on some of that stuff. Like, I'm fascinated by what people were able to do because they were thinkers back then. All right. So given this diagram, I love this diagram. We're going to talk about this diagram a lot, but I need you to see the relationship between a lot of these angles. Okay, 1 and 5. What are they? Say that loud. Okay, 1 and 4. What are they? 3 and 6. What are they? 3 and 7. What are they? Yeah. So here's the deal. We're moving from a unit on parallel lines to our next unit today, which is triangles. Do you see the triangle?
Yes.
So the triangle has 3 angles in it. It's our basic polygon. And we're going to study polygons with more sides and angles, 3, 4, 5, 6, 7, on up. But the triangle is our most basic of shapes. Do you see angles 2 and 5 and 6? One of the first theorems that we're going to learn about a triangle is that the sum of the interior angles of a triangle is 180 degrees. What is true about the measures of angles 1 and 5? Stay with me here. What is true about the measures of angles 1 and 5? They are congruent. 5 is inside the triangle, 1 is not. What is true about angle measures 3 and 6? They're congruent. 6 is inside the triangle, 3 is not. If I asked you the sum of angles 1 and 2 and 3, what would you tell me? 180 degrees because they make a straight angle. With your group, tell me why the angles sum inside a triangle is 180 degrees. Turn and talk about what you notice. That's an
Wait, what are you looking
Did you get it, Forrest? Okay, I'm going to walk you through it. Ready? Forrest, what is the sum of 1, 2, and 3? Angle 1 plus angle 2 plus angle 3 is?
180.
180. 1 and 5 are congruent, right? 3 and 6 are? So if 1 plus 2 plus 3 is equal to 180, can I substitute 5 in for 1? Can I substitute 6 in for 3? So isn't 5 plus 2 plus 6? Do you see it now? Oh, right? Do you see it now? So how cool is it that we can use our parallel lines, our alternating interior angles, to go out and prove that? Hey, I'm going to push you one step further. Ready? Talk to me about the sum of 4 and 5. Call it out. 180, because those angles are supplementary. They're supplementary because they are in linear pair. Okay. So 4 and 5 are adjacent angles whose non-common sides are opposite rays. Got it. Because they're a linear pair, I know the linear pair postulate tells me they're supplementary. Because they're supplementary, their sum is 180 degrees. Everybody with me on that daisy chain? Okay. If 5 plus 2 plus 6 is 180, this one's a stretch. So keep up with me here. Ready? Watch, watch, watch. If 5 plus 2 plus 6 is 180, and 5 plus 4 is 180, what is the relationship between 2 and 6 and 4? Talk in your group. Maggie looks at her group, she goes, they're congruent. And then she moves on. Why are they congruent?
Are you asking me?
Yes, I am.
Oh, okay, because if 2 and 6 added together substitution math. I'm great at this. 5 plus 4 equals 180, and 5 plus 2 plus 6 equals 180. Then 2 and 6 equal.
Yeah. Yeah. So think about this. If we have the measure of angle 5 plus the measure of angle 4 is equal to 180, the measure of angle 5 plus the measure of angle 2 plus the measure of angle 6 equals 180. Do you see that 4 has to be the same as 2 plus 6? So I didn't even hand out any notes yet, and you just learned our 2 theorems that we're doing today. Triangle sum theorem. Sum of the interior angles of a triangle is 180 degrees. Exterior angle theorem. The exterior angle is equal to the sum of the 2 remote interior angles. Pretty cool, huh? Okay. Would you please take your triangle? And take your triangle. Would you please draw and label angle 1? Draw and label angle 2, and draw and label angle 3. So we have 6 different classifications when we talk about angles. 3 have to do with sides, and 3 have to do with angles. Our vocabulary for our sides is whether it's equilateral, isosceles, or scalene. Scalene means all 3 sides have a different length. Equilateral means all 3 sides have the same length. Isosceles means 2 of the sides have the same length. Make a guess about what your triangle is. Equilateral, isosceles, or scalene. Okay, now let's talk about the angles of your triangle. We have 3 different vocabulary words that have to do with the angles of your triangle. Either your triangle is a right triangle because it has a right angle. Your triangle can be an obtuse triangle because your triangle has one obtuse angle. Your triangle can be an acute angle because all it has is 3 acute little angles. Take a look at your triangle. Does it have one right angle? Then it's a right triangle. Does it have one obtuse angle? Then it's an obtuse triangle. Does it have 3 acute little angles? Then it's acute. So we can talk about classifying and naming our triangles by what we see with respect to its sides and with respect to its angles. All right, let's get some notes out of the way. A polygon is a closed figure with sides, no curves, and every vertex has no more than 2 segments coming from it. No curves, it has to be closed, and every vertex can only have exactly 2 segments meeting at it. Take a look at these 5 polygons, and with the group, tell me which ones are not polygons. Put across X amount, go. Do we agree? Do we agree? Okay, let's start with the easy one. Do you see the curves? Do you see the curves in B? That means it's not a polygon. How about this one? Do you see how it's not closed? That means it's not a polygon. But I hear some conversations about A. What the? What's going on with A? What do you think, Maggie?
It has, the vertices and the angles with more than 2 segments hanging off.
Yeah. So this whole thing with vertices with greater than 2 segments, that's what's happening here. Do you see these 3 segments here? So that prevents that shape from being a polygon. That shape is not a polygon. So that's the kind of quiz question you either get right because you're paying attention right now and you study it and you review it, or that's the kind of quiz question where I get you. And I don't like to get you. Go ahead.
Wait, so if that line in the middle wasn't there, it'd be a polygon?
If that line in the middle wasn't there, if I had this is a closed figure with sides, that's fine. Got it?
Yeah.
I know Christian's thinking today. All right, a triangle is a polygon with exactly 3 sides, exactly 3 angles. When we name our polygon, we name them by our vertices with capital letters, and nobody cares what order you go in. So this triangle is triangle ABC, triangle BCA, triangle CAB, and there's 3 more names. See if you can come up with a name that I don't have listed here. Talk in your group. Go. I heard BAC from this group here. Who else has one? CBA. Anything else? ACB. Okay? Yeah. As long as you have 3 letters together, you're good. Hey, here's the facts. We can name a triangle by sides. We can name a triangle by angles. Your triangle is either scalene, isosceles, or equilateral. If we're talking about sides. Here is the kicker that you're going to get hung up on. Isosceles triangle has at least 2 congruent sides. A special kind of isosceles triangle is an equilateral triangle. I'll say that one more time. A special kind of isosceles. So every equilateral triangle is also isosceles. So an isosceles triangle has at least 2 congruent sides. Equilateral exactly 3. So if you wanted to be sure about your triangle, you all have rulers inside your baskets. You can measure them. I'm gambling most of you have scale. Anybody feel like they have an isosceles triangle? Anybody feel like they have an equilateral? I just cut them randomly, so if I end up with an equilateral triangle, I'm going to go play the lottery. Because that's pretty hard. That's pretty hard to figure out on the fly. All right. When we're talking about your triangle angles, this is your second thing to pick from. If you have 1 obtuse or 1 right angle, that's making that triangle right away a right triangle or an obtuse triangle. And if you think about what we just did with each angle, with each triangle being 180 degrees total, that makes sense to you. I can't have 2 right angles because then I don't have any degrees left for my third angle. See what I mean? I can't have 2 obtuse angles because I can't have 2 angles worth more than 90 degrees. So just having 1 obtuse angle, 1 right angle is enough to classify that. And then for an acute triangle, all 3 are cute little angles. So here's the deal. When you're looking at your triangle, if you're not sure, did you know that every single time a teacher gives you a piece of paper, they gift you with not 1, not 2, not 3, not 4, but 4 right angles? Every time a teacher in this building hands you a piece of paper, you should say thank you, because that teacher just gave you 4 right angles. So take the triangles, take the angles of your triangle, and compare it to your paper. So mine are kind of obvious, but if I have a triangle like this, and I'm not sure if it's a right angle, I'm going to hold it up to, yep, that looks pretty good. I'm going to classify this triangle as a right triangle. Anybody feel like they got one of the right triangles? Raise your hand. There you go. Okay. Anybody feel like they have an obtuse angle? The obtuse angles, yeah. That's how you see, let me see if I can find an obtuse angle. That's how you can see, and like I said, all you need is one. But as soon as I compare this angle to my right angle, look at that gift I get. Every single time I get a new piece of paper, wham, 4 right angles. And I can see that this is bigger than that. So if I have an obtuse or a right or 3 acutes, that's how I classify. And when you classify your triangles, you need one word from each of these. And nobody cares which one you say first. Acute right or right acute? No, not possible. Right scalene or scalene right? That's possible. One word from each category. Does that make sense? Share with your group mates what your triangle is. Go. Okay, come back. All right, interior angles, angles that are on the inside of the triangle. That's nothing new. Exterior angles are going to be these angles that are outside of your triangle. So, and we get an exterior angle by extending one of our side lengths. So when we extend the side lengths, we end up with an exterior angle. We're going to talk more about that in a minute. Our remote interior angles are going to be the 2 non-adjacent interior angles to that exterior angle. So if this is my exterior angle, check this out. Here's my side of my triangle that I've extended. If this is my exterior angle, my remote interior angles are going to be these far away interior angles. And those are the ones that we said were congruent to that exterior angle measure. Hey, we can't go on for one more minute until you know what these symbols mean. What do they mean? Yeah. So these symbols mean that these sides are congruent. If they're congruent, that means they have the same measure. If I have this triangle with 1, 2, 3 congruent measurements, classify that triangle by sides. I'll say it one more time. I have this triangle with 3 congruent measurements. Classify it by sides. Yeah, it's going to be equilateral. So this is an equilater, equilateral triangle. Okay, so now I want to classify it. That's it by sides. Classify it by angles. What do you think? Yeah. They're all acute angles, but here's something special that you need to add to your list that we want to make sure you know. If we have an equilateral triangle, it's also going to always be equiangular, equiangular. Every equilateral triangle is also equal angular. If I have 3 equal sides, I'm guaranteed to have 3 equal angles. Bonus point, what's the measure of each of these angles? You're so close. I think I heard it. 60 degrees. 180 divided by 3. Hand in the air or just, no. All right, how about this triangle here? What's this triangle guaranteed to be? Classify it by sides and angles. Isosceles. We don't know anything about this last side. Doesn't have a marking on it, so we're going to call it isosceles by sides. Talk to me about angles. We're thinking acute, but without our next theorem, you don't know. So we're going to hold on to this and come back because it's acute, but we'll talk about why in just a minute. All right, do me a favor, look over the whole page. Talk to your group mates. One thing you want to make sure you remember from this page. Go. Can't say everything.
I think I can remember it too. Also, like the pump my ears. It's like this. The cute is like a cute little shop.
Christian, what did you want to remember? So if there's any new vocabulary words, I'm not surprised if that's what you might pick. I liked how Adney said he wants to make sure that he picks one from each box. When it comes to classifying, you have to pick one from each box. If any of these words are new to you, that's the one that you want to make sure you get. Forrest says, I want to make sure I remember this equal angular. That's not up here. So maybe when we talk about these acute triangles, Forrest wants to go ahead and add that word up here, EQUIANGULAR, to make sure that that works. All right, let's talk about the back side. So some practice, I would like you and your partners to classify each triangle by both sides and angles. And then here is a challenge for you. Sketch each triangle. And I want you to find, now, we think there's two. I'd be surprised if we can find a third that's impossible. Find which two are impossible. So with your group mates, please go ahead and do that. On your mark, set, go. So I'm completely loving the vocabulary that I'm hearing. I'm completely loving. Which two are impossible? Anybody's absolutely, positively confident, I know this one is impossible, and be prepared. I'm going to ask you why, and your answer has to start with because, and then that's your justification. Olivia, wait a minute. There you go.
Okay, so right equilateral would not be possible because if you were to have three right angles, the shape would have to be classified as a square because those angles would be congruent at that point.
Did you hear what she said? If I had a right equilateral, as soon as I go to make all of my angles right angles, I've got myself a square, and that is not a triangle. Nice thinking. Next one, James, what do you know?
I thought the obtuse equilateral was impossible.
Yep, keep going.
Because if you just made one with all three sides, the angle right here, like this one, would always be longer than the other two.
Okay. So if I have two obtuse angles, they're both open, right? They don't come together. So I'm not gonna be able to make. So the interesting thing was where Mr. Logan and I got this activity, they said 3. And there's not 3. The rest of them are all possible. But if I told you 3, would you be looking for a third one? Because I'm over here listening to a conversation about acute scalene. And I'm over here listening to a conversation about obtuse isosceles. And what you're thinking and what you're doing and grabbing the pencils and the rulers and drawing is great thoughts. Should we keep it 3 so that we keep thinking and looking and trying? Did you figure out your obtuse isosceles in the back? Did you? Yeah? Because an obtuse isosceles is going to be where this angle is obtuse, but then these sides are the same. Are we okay with that? Did you figure out acute scalene? Yeah? So that's just going to be a triangle that has 3 different sides. And that looks more isosceles. So maybe that.
Oh.
Right? Oops, that looks more. So I have 3 different side lengths and 3 different angle measures. acute isosceles, I can have an isosceles triangle where these two sides are going to be the same. Our acute equilateral is also going to be equal angular. Somebody said they wanted to remember. Was that you, Aiden? Where you wanted to remember the word equal angular? Practice using that word. An obtuse scalene angle, an obtuse scalene triangle, 3 different side lengths with an obtuse. Hey, our right scalene is the foundation of so much of what Pythagoras had going on. If we had a 3 and a 4 and a 5 triangle, we're going to talk about a lot of that. And a right isosceles triangle, again, is where these two sides are the same, and we're going to learn that these two sides are going to be 45-degree angles. And that's a huge special triangle that we talk about lots and lots and lots. Hey, remember I told you already learned the 2 theorems just from our warm-up? Here they are. The triangle sum theorem says the sum of the measures in a triangle is 180 degrees. Grab some colored pencils from the basket in the middle and interact with this diagram, showing yourself that these angles are alternating interior angles, and that when they are each added to angle 2, that proves the triangle sum theorem. Hey, I got one more thing for you. Remember your triangles that I told you to label angles 1, 2, and 3? Would you please rip off each angle? Rip off each angle. Until you're left with this sad looking chewed up piece of paper. Have your 3 angles like thus. And what I would like you to do is arrange those 3 angles in a straight line.
Straight.
Proves that those 3 angles measure up to 180 degrees. Spin them, manipulate them, match them up. Do what you need to do to prove that the sum of the measures of inside every triangle is equal to 180 degrees. Brian's got it. Forrest has it. Maurice has it. Mag's got it. Take the sum of those angle measures. Hey, this is what we call a physical proof in geometry. If I add the measure of angle 1 to the measure of angle 2, if I then add that to the measure of angle 3, I've just proven that the sum of the measures of the interior angles of a triangle are equal to 180 degrees. And we all have different triangles. Some of us had acute, some of us had right, some of us had obtuse, and it worked for all of them. Hey, here's a new vocab word for you, the word corollary. And we'll talk about it when you get back from lunch. Hey, can you take your triangle trash and throw it out on your way out so I don't find pieces of triangle all over the place? I'll see you when you get back from lunch.